Hello and welcome to our lab on rotational equilibrium. Rotational equilibrium means that something does not have an angular acceleration. In other words, the speed at which it's rotating is not increasing or decreasing. And so that can either be rotation at a constant angular velocity, in other words, a constant number of radians per second, or not rotating at all. Would be a special case of rotational equilibrium. But if your radians per second is increasing or decreasing, then you have an angular acceleration and you do not have rotational equilibrium. And so in this lab we're going to be dealing mostly with the idea of torque. And so one way that you can cause rotate an angular acceleration is to apply a torque. And a torque is a force acting at a distance. And so the equation that we use for torque is this. Torque, this is sort of a T, it's a tau, it looks like a T with a wavy top, is equal to a force applied at a distance. But as it turns out, there's something more to it. You know, if you're opening a door, or you want to close the door, what do you do? Well, if you're going to open a door, and so here's our door. Here are the hinges of the door. If I wanted to open that door, the reason the door handle's over on the right side is because we're trying to get it at a far distance from the axis of rotation. And so this is our distance, r. And so we apply a force over here, and the torque is F times r, force times distance. If we put the doorknob over here near the hinge, we have to really pull hard to open that door. But that's why the doorknob goes on the opposite side from the hinge. Now you know. Now, as it turns out, to get the maximum torque or force on the door, I push this way. But let's say the door is open. Okay, I'm standing to the right of it, and I give a push this direction. And I'm pushing on the side of the door toward the hinge. Well, guess what? I'm not going to open or close the door. I'm just pushing into the hinge. And so even though I'm applying a force at a distance, I'm not applying any torque that can cause the door to move. And that's because the angle at which I'm applying it is all wrong. And so torque is equal to force times distance times the sine of the applied angle. And so when that angle is 0 degrees, like me in the door here, no torque is created. However, when the angle is at 9 degrees, I walk around here and push that direction, then I get maximum torque. And so for the same force, I get varying degrees of torque anywhere in between. Now in our case, we have a meter stick. And so let me kind of start over here. We're going to have a meter stick. And the meter stick is supported at a fulcrum. Okay. So here's the support of the meter stick. Right about near the 50 centimeter mark. And so in order to find where that center of the meter stick is, I take my meter stick and I have this little clip here. I'll show you what that looks like. And with the thumb screw part of it down, this has a little screw on the bottom of it. Okay, with the screw part downward, these little knife blade edges are pointing downward as well. I can slide this onto the meter stick, just like that. Run it to about the middle, and I can find the center of mass of the meter stick by placing it on a fulcrum. Here's the fulcrum. I'll get it off the table a little bit. We'll see why later. With a couple of blocks. And so setting that there, I can adjust this until I've found the center of mass of the meter stick. In other words, if that center of mass is supported by this fulcrum, then I get no rotation. And so it looks like I need to come this way a little bit. And so as it turns out, the center of mass of this meter stick is not right at the 50 centimeter mark. It's a little bit to the left of it. So I want to record that center of mass. And so now, let me just show you with this, practically first. I want to apply a torque. Now the way I'll apply a torque is I can push downward over here. And that, when I push downward over here, that applies a torque that's in this direction, or a counterclockwise torque. And conventionally, this is called a positive torque. A counterclockwise torque is positive. Or I could push upward over here. That would apply a clockwise torque. And those torques are said to be negative. Now, conversely, over here, I can push downward and create a, you're right, negative clockwise torque, or upward on this side to create a counterclockwise positive torque. So the way I want to create my torque is using a weight, a mass. And so I have a little mass clip. It's just like the fulcrum, except now I want to point the thumb screw upward, and I have a little clip that's dangling downward, a little hanger. And I can put my mass hanger on it. And so now I have two things, the mass clip and the mass hanger, and then I can put a mass on it. Now I've got three things, a mass, a hanger, and a clip. And I'm sort of telling you what those three things are because you have to add all of that up when you're determining torque. So I want to keep this clip and hanger together, and let me find the mass of those using my handy pan balance over there. And the mass of those two together, it's around 75 grams. And so I want to keep these two together. Now I know what their mass is, because I want to be very precise. I want to keep up with all my masses. So I hang this on it. I can mass it over here, or just take this to be 100 grams to the nearest tenth of a gram. And now by sliding it on the end of the meter stick, I am applying a torque. So I'm applying a force, and that force is gravitational. It's the mass of these three things multiplied by g, which is 9.7953 meters per second squared here in Boone. And sure enough, if I release this, I have an angular acceleration in the negative direction, clockwise. And so to establish rotational equilibrium, I have to apply a torque here that's upward. Okay? And my equation tells me that this is my upward torque. If I put it closer to this axis of rotation, I'm applying a force upward that's greater than the weight of this. If I put it out here, though, I'm applying a force upward that's less than all of this because of the way my equation works. And so another way I can apply a counterclockwise or positive torque is to put another mass, clip, hanger, and mass on the other side and push downward. And at that point, I've established rotational equilibrium. Now, rotational equilibrium tells me that all of my torques, if I add up my clockwise torques and my counterclockwise torques, my total torque, my net torque, is equal to 0. Similar to the way that when you add up all your forces, if something has translational equilibrium, which means there's no translational acceleration, it's not accelerating, its velocity isn't changing, that means you have no net force. All of your forces sum to 0, and you have constant velocity or 0 velocity, no acceleration. When the same way, if we have rotational equilibrium instead of translational equilibrium, that means not that we have no net force, but that we have no net torque. And so here we go. We can apply a force downward. Here's our mass. And our torque is equal to the force, which is gravitational, mg, times r, the distance. And the distance r is to the axis of rotation, r, times the sine of theta. Well, this is pretty easy. When my meter stick is balanced and the masses are hanging down, the masses are hanging in a way that's perpendicular to the lever arm, and so theta is 90 degrees. So this goes to 1. And so I don't really have to worry about what theta is, or sine theta is. It's always going to be 1, because theta in this experiment is always 90 degrees. If we were to use a force probe or some other thing, let's say change the direction, then we'd have to worry about theta. That might be a fun addition that you could look at it in consideration. And so to balance this, we could put another torque. Maybe have a mass hanging here. Let's put a bigger mass closer in. Here's R. And again, we have another torque. And so rotational equilibrium says that the torques in the clockwise direction, T subscript clockwise, are equal to the torques in the counterclockwise, CCW, or in other words, the clockwise torques plus the counterclockwise torques equals 0. That's the situation required for rotational equilibrium. And so in this lab, what we're going to do is take a look at some of that. We're going to tell you where to put a mass, or maybe tell you to what value of mass to put at a certain location, maybe multiple locations, and then you have to calculate based on these ideas that for rotational equilibrium, torques must sum to 0. So if we have too much clockwise torque and it's rotating this way, you'll have to calculate maybe how much mass to put at a certain distance, or at what distance do you put a certain mass in order to make your torques sum to 0 and set up the situation where you have rotational equilibrium. Now up to this point we haven't talked about the mass of the meter stick. Now this meter stick itself has mass, but in terms of torque, when you look at the torque exerted by a mass and you're measuring that distance R, that distance R that we showed is actually the distance from the center of axis of rotation to the center of mass of the hanging mass, or along the lever arm to where that center of mass is acting. And because we put the center of mass of the meter stick right there at the fulcrum, then R has a value of 0, and this meter stick applies, the mass of the meter stick applies no torque to the system. So that's one way we can neglect the mass of the meter stick in this experiment. All right, so the math is really straightforward in this, and the numbers come out great. We should get really good results in our experiment on rotational equilibrium.